Welcome to my final year project thesis presentation. The title of the thesis is to design, build, model, stabilize and swing up a rotary inverted pendulum. So a pendulum is stable when it's pendant and it's unstable when it's in the inverted position. This means that to maintain the upright position, external control must be applied. In this project, a motor was the actuator which moved the pendulum's pivot point underneath it to stabilize it, and this was done by implementing two PID controllers to calculate the motor output based on the pendulum angle and the arm angle. So those are the aims there of the project, and all of these aims were achieved. This is the presentation layout here. So it's split into 5 parts. Literature and key findings, the build, coding, modeling, and then finally testing. So we'll start with the literature section. Different control strategies were investigated for stabilization and swing up, with popular approaches being LQR and PID for stabilization and energy methods for the swing up. Some important considerations to make when designing a controller are whether the model will be linear or non-linear, or if there is even a need for a model at all. Performance characteristics such as settling time and overshoot, and a decision on the robustness performance trade-off. Onto the modeling section then. Typically a model of the physical system is simulated with the controller of choice before testing on the actual rotary inverted pendulum rig. Most control strategies require an accurate model, but not all. For example, fuzzy control does not require an accurate model, and PID does not require a model at all. These are some of the commonly used programs for modeling. Simulink offers many toolbox add-ons which can make the process easier and more accurate. For example, one method found for modeling a motor involved recording the motor's response and using Simulink's design optimization toolbox to emulate the response and create a model. Research was done into what sort of components would be required to realise the project. 2 angles had to be measured and a motor was required for actuation. The controller did the processing and converted the angle inputs into an output for the motor via the motor driver. The controller of choice was an Arduino Mega because of its easy to learn coding language and availability at the time of design. And some various other essential components were couplings, pulleys and bearings. Moving on to the build section then. First of all, this design specification was created to set physical and performance specifications for the project. This design specification was followed throughout the project to ensure that the final product could achieve its goals. So then these 3 design concepts were created: counterweight, threaded bar and compact. Each had their own advantages and disadvantages, and to decide which of these features were the most important to carry into the final design, this Pew matrix was made. So each of these designs was ranked on various physical and performance parameters, and the compact design scored the overall highest. The most important findings were that the simpler the design, the better, and that the motor should have a high responsiveness and acceleration. This meant transmitting torque directly to the arm, not through a belt, and Furuta, the creator of the rotary inverted pendulum, pointed out that the absence of a belt in a design is good because it's just one less component to model. So taking these things into consideration, a prototype build was made. This prototype was built primarily for 2 reasons. One reason was to have something physical to practice and learn coding with, and the other reason was to find problems early on so that they could be avoided in the final build. This prototype only took about 3.5 hours to build, and it was well worth the time. Some of these early problems are listed here with their solutions. The most important finding was that this motor needed to be upgraded to produce more torque, and so that swing up would be possible. Just to point out some of the manufacturing processes, there was plasma cutting for the base, lathing and topping for the couplings, CAD modelling of course, and quite a bit of 3D printing. Now presented is the final build, with the rig on the right and the CAD model on the left. Here is a functional block diagram of the system to clarify the interaction between components and the electronics. The components in red represent the electronic components which act as inputs and outputs. The electronics part of the project was quite big. The photo in the center is the actual circuit, and on the right there is a schematic for clarity. The black 3D printed case in the photo on the left there was designed to aesthetically contain the electronics and ensure that no wiring became loose. Grills were incorporated to encourage heat transfer from the chip, and the motor driver's heatsink protruded for the same reason. The case clipped neatly onto the side of the rig with access points for the USB port and the reset button on the Arduino. This brings us then onto the coding section of the presentation. So I had to learn Arduino coding from scratch, which was quite a lengthy process. I wrote my first program on November 18th. This was a simple program which alternated blinking LEDs. 5 days later, I got the encoder library working and wrote code that could control the brightness of an LED based on the pendulum position. Then on December 3rd, I achieved partial stabilisation of just the pendulum, but without any consideration for the arm. I realised that incorporating a second PID could be the solution, and on January 24th I implemented 2 PID controllers as shown in the block diagram above. After achieving stabilisation control on the prototype, I decided to make the final build. The clip there is the final solution, and the flowchart of the code is shown here. In the setup section, the preset PID gains are red. A 2-second pause gives time to get some distance from the pendulum before it swings up, because the swing up, as you can see, is quite violent. Into the loop part of the code then, the pendulum angle and arm angles are measured, and the stabilisation controller output is calculated, and a voltage is outputted to the motor. After collecting data, the cycle repeats. The swing up controller is only run on the first run through of the code. The swing up works by taking advantage of the high torque motor. By applying a step input voltage to the motor, the pendulum swings up to the inverted position. Once it is nearly upright, a delay function assists in lowering its velocity, and then on a timer, stabilisation control is switched to. So the magnitude of the step input which was required to swing the pendulum all the way up was determined heuristically. Now moving on to the modelling section of the presentation. So first of all, I determined the equations of motion based on quite a few assumptions, and these equations of motion were derived from Newton's laws of motion, and the constants were determined by taking measurements from the actual real rig and from the SolidWorks model. But this model was not actually simulated because a more accurate method for obtaining the model was found. Simulink Multibody is a Simulink toolbox which allows you to export the SolidWorks CAD model into Simulink, and it generates a mathematical model and animation. You can see here that the angle readings were taken from the shaft joint and from the pendulum encoder joint. A free swing test was done to compare the real and simulated angle outputs, and the results were found to be very similar. Many different methods were attempted for modelling the motor, but in the end, by assuming it to have a first order response, the transfer function was determined by measuring the angular velocity output and the time constant. Attempts were made to emulate the stabilisation controller in Simulink using the motor and plant models, but due to inexperience with the software I could not get a similar response. I found it especially difficult to incorporate the H-bridge and PWM circuits into the controller model, and also I was having difficulty setting reference angles for the joint positions, so for these reasons I could not successfully model the stabilization controller. We're at the final section of the presentation now, which is testing. Some tests were performed on the system to ensure that the objectives in the design specifications were met and to gain a better understanding of the control system. The graphs in this section are of the pendulum and arm angles against time, with the pendulum being the blue line and the arm being the red line. It was difficult to quantitatively analyse the system since two PID controllers were incorporated. Settling times and overshoots couldn't be determined. For this reason, the performance was analysed based on responsiveness, stability, the period of oscillations, the size of the angle deviations, and the nature of the oscillations. Firstly, repeatability tests were conducted. The swing-up controller proved to work consistently, and stabilisation controller could be left on for 3 minutes without any change in performance. One of the main tests then involved changing the PID gains individually. A key finding was that either the arm position or the pendulum position dominated the output. The extremes can be seen in these clips on the right here, where the arm is dominant in this one and the pendulum is dominant in this one. With this in mind, the tuning process became much more logical. Test D tested the disturbance recovery and robustness of the stabilization controller. The system was found to be able to recover from large disturbances of 10.4 degrees, which was greater than the 3-degree aim set out in the design specification. The robustness test then just involved attaching an off-centered mass to the pendulum, and the system was very capable of handling this. Finally, the simulations were compared to the real system. A free swing test was performed where the pendulum was held in the upright position and released. For the DC motor test, a step input of 8.16 volts was applied to the motor, and the angular velocity response was recorded. In both of these tests, the models produced similar results to the real response. So to conclude then, the design specification was met and a rotary inverted pendulum was produced. The stabilization and swing-up controllers were successfully designed and implemented, and although the controllers weren't simulated, the system's components were, so the actual rig and the motor. So all the performance specifications were met. It was difficult to compare this rotary inverted pendulum to those in research due to the use of two PID controllers. It was determined, however, that this system could outperform many other controllers when subjected to disturbances. This robustness is a known benefit of PID controllers. It is also to be noted that the swing-up routine used in this project was not feedback-based, so the swing-up was much faster than most in literature, although not robust. And if there was any future work to be carried out with this project, it would be interesting to see different control strategies being implemented, such as LQR for stabilization, or an energy forcing function for the swing-up, which is something which past DIT students had done. Also then, stiction in the motor could have been compensated for better, and then also it would be interesting to see the actual controller simulated. Thank you for your time.